All right, everybody, and moving on now into the second part of our notes here on 4.4 and 4.6. So I just kind of called this putting it all together because these two problems that we're going to do, and I'll warn you, it's just two problems, but they're going to take a pretty significant amount of time and work here. These kind of encapsulate everything that we talked about in the end of 4.3, the beginning of 4.4, and then all this 4.6 stuff as well. We're going to be using both the first and the second derivative in order to figure out the most detailed way possible here in order to come up with the essential information we need about that graph, both in terms of critical points, extreme values, and points of inflection. So by piecing all of that info together, we should be able to get a pretty good sense of what our graphs look like. So if you notice here, this particular function, g of x equals x to the fourth minus 4x cubed plus 16x minus 10, should look familiar because this is the same function that I used in our notes at the end of 4.3, where we talked about intervals of increasing and decreasing. And also earlier, I believe in this same section right here, we did that same function right on this one right here. So actually, I'm going to save a little bit of time, especially since this is on video here, and just kind of tie everything together here. And you guys are going to have to pardon me for just a second. I'm going to pull up my notes here, not on my... Here we go. All right, not on my iPad because I would lose this file if I did, and it's a big pain in the butt. But I'm going to do this on my Chromebook, right, or excuse me, my laptop in front of me here. So if we take a look at this problem here, all right, this is what we went back to and we were working on in section 4.3, and we had already found the intervals of increasing and decreasing. So if I'm going to just kind of cheat on this one a little bit, we were looking at, let's take a look. Sorry guys, I'm trying to find this function in the old one here. All right, well let's go ahead and jot a few things down. So we knew, I guess I'll write this again, that our first derivative, oh, that's not what I wanted. All right. Go away. All right, our first derivative here, g prime of x, was equal to, we had a 4x cubed, a minus 12x squared, and a plus 16. We set that equal to 0, and we got two critical values out of that. And those were, I believe, and I'm sorry, I'm having a hard time finding this now, I think at x equals, was it -1 and +2? But I want to double check that before I write that down incorrectly. So let's try that again here, guys. Yep, that was it. X equals -1. Sorry, we found that. X equals -1 and x equals +2. And what we found then, everybody, let me go ahead and do just a condensed version of this sign chart here. And if you're not sure where this came from, go back and look at the video from the second part of 4.3. And what we found here is that on this first interval, g was decreasing. On the second interval, g was increasing. And on the third interval, g was still increasing. So one thing that I'm not sure that we wrote down in the 4.3 notes, but we can go ahead and deduce right now, is that at x equals -1, our function's behavior changed from decreasing to increasing, and that was because our derivative, our first derivative, changed sign from negative to positive. That tells us something important, everybody. That tells us that g has a minimum at x equals -1. Okay, in a minute, we're going to figure out what that y value is there as well, but I don't know that we're going to do that just yet. I want to do that a little bit more efficiently later on. Now, you might be tempted to assume then that because there was a minimum at x equals -1, that would guarantee, or at least tell us that we have a maximum at x equals 2. That's incorrect, and we can tell that by looking here at the fact that prior to x equals 2, g was increasing, and that after x equals 2, g isn't decreasing now, it's still increasing. So that tells us that g does not have either a maximum or a minimum at x equals 2 because the behavior of the function does not change. So we know that. Okay, the other thing, let me just go back to this very last problem that we did here, and let's now focus on this fact that we came up with right here. Okay, again, in looking at the graph, oh, this is a disaster. Boy, no great way for me to, I guess I'll highlight this. We knew that the function was concave upward to the left or prior to x equals 0. Then we knew that after x equals 0, the function changed and was now concave down, and then after x equals 2, our function was now concave up again. So, focusing on this fact right here, guys, we know that we've got points of inflection at x equals 0 or at x equals 2. So I'm going to go ahead and write that information right down here. So G has a point of inflection at, and we knew that it was at x equals 0. And I'm going to go ahead and write that as an ordered pair here. So it's going to be 0 comma something. Or another one we said at x equals 2, which is going to be 2 comma something. And while I'm at it, let's go ahead and deal with this here, guys. In looking at the sign chart from both the first derivative and then, of course, my second derivative sign chart, which is located right here, we came up with a grand total of 3, what I'm going to call points of interest. Okay? I mean that a little bit differently from critical points. We've got a minimum right here at x equals -1, and then we have 2 points of inflection at x equals 0 and x equals 2. We're going to take those 3 points of interest, and we are going to evaluate the original function g of x at each of those x values to figure out the locations, the coordinates of these 3 points of interest. And then, when we're going to put everything else together right now, we should be able to come up with a pretty decent graph of what this function looks like. So, what I'm going to do is I'm not going to ask you guys to evaluate a whole lot of 4th degree functions by hand for anything beyond 0 or 1 or anything like that. So we are going to go to our calculator here. I got a blank page, and I'm going to begin here, everybody, by defining what that function is in the calculator here. So I'm going to do it this way. We are going to define, and we're going to call this function f1 of x. Okay, looking something like that, and it is going to equal, here we go, and the function in question was, let me go back to my calculator page here, it was x to the 4th power, and then I've forgotten, minus 4x cubed plus 16x, so a minus 4x cubed, gotcha, plus a 16x, and minus 10 at the end of all that. Okay, so that was our definition for f1 of x, and that's done. And now we wanted to evaluate that function at these 3 important values of x. So the first one I had right here was that the minimum was going to occur at the spot where x was equal to -1. So we'll go here and we will ask the calculator just to, the f is hiding here somewhere. Okay, there it is, f1, and we're going to evaluate that at -1. And that got us a y value of -21. So let's go right back over here and put in a -21. And we now know the exact position, x coordinate and y coordinate, of our 1 minimum value. We also have a point of inflection when x is 0 and x is 2. So let's go ahead and evaluate both of those. So again, f1 of 0, really didn't need the calculator for that, did we? That's -10. And while we're here, f1 of 2, and that is going to get us 6. So 0, -10, and 2, 6. Those are the coordinates then of our 2 points of inflection. So what is really, really important now, everybody, is that we now know the coordinates of our 1 minimum and our 2 points of inflection. And those 2 points right there should give us all of the information that we need in order to come up with a pretty good graph of this function. So let's see what's going on here. You'll notice I just left this as a blank graph, nothing too exciting here. And so without thinking too hard right now, I want to leave a little bit of room on the bottom or the side of this graph. Doesn't matter too much. I think you'll see why in just a moment, but let me just start with this one right here. And you'll notice, guys, I'm not going to spend a whole lot of time trying to make sure that my coordinates are exactly perfect. We're really just coming up with kind of a rough sketch of what this graph looks like, but it should be pretty accurate. So the 3 points that we know here are -1, -21. That is by far the lowest point I needed to come up with here. So -1, let me just do a -1 here, and I'm going to say that -20 is way the heck down here somewhere, and we'll go just a little bit below that. And then, so let's see, we had a minimum at -1, -21. So let me go ahead and plot that just a little below that point right there. So that's our minimum. And then we had points of inflection at 0, -10, and 2, 6. So 0, -10, -10 would be right about there, gotcha. And then 2, that would be 1, that would be 2. And just trying to get my spacing consistent, I'm thinking that 6 would be somewhere right about there. So 0, -10 was a point of inflection, as was 2, 6. Now we've got 3 points right there. Boy, the geometry teacher in me almost thinks that those points might be collinear, but I don't think that they are. Looking at the slope between this point and this point, looks like we've got a slope of, I think that is going to be 11. And then from here to here, that slope looks like it would be what, guys? 16/2 looks like it would be 8. So close, but no, the points are not collinear, and that won't usually be the case. But now what we have to do, everybody, is using these 3 points, the only points of interest we were able to come up with, what we now need to do is read 2 sign charts simultaneously. And I know this is going to take a moment right here, but I'm going to essentially redraw my 2 sign charts here very quickly, one above the other. So the first sign chart is the one that comes from the first derivative right here. So we've got -1 and 2. So I'll go ahead and put boxes around those. Okay, and this was kind of a 3-level sign chart right here. And I'm not going to put all the details. I'm only going to put the results of this sign chart. Our function was decreasing, increasing, increasing. That's what we need to know. G was decreasing, G then increased, G then increased as well. And the second thing we're going to do now is put our second derivative sign chart, which was right here, everybody. We got 2 potential points of inflection at 0 and 2. So I'm going to put those in here, and you guys are going to see where I'm going to do this here. X equals 0, I'm going to write here somewhere in between -1 and 2, but I'm going to try to put x equals 2 here directly below the other x equals 2. So maybe you can kind of see what I'm going for right here. When we put these two together, it's almost like a little number line. -1 is furthest to the left, 0 is in the middle, and the 2's line up. And the result of the second derivative sign chart are what I've highlighted right here in yellow. Concave up, concave down, concave up. So concave upward, concave downward, concave upward. All right, everybody. With those 3 blue dots, and then the information that is in those 2 purple sign charts over there, we're going to be able to draw this function with a reasonable degree of accuracy. All right, let's see what we mean here, guys. The furthest interval to the left right here, guys, would be all values of x that are less than -1. So we need to be able to read 2 things out of this sign chart. When x is less than -1, what's our behavior and what's our concavity? Well, our behavior here is that g is decreasing, but of course that's read from left to right. So way out to the left of this point right here, guys, our function needs to be decreasing, going down from left to right, but it also needs to be concave upward. So I always find that easier to kind of draw backwards. From my minimum here, from right to left, this function is going to look like it's increasing. It's really decreasing from left to right. So I'm going to draw this thing then going up in this direction, and it's got to be concave upward. So let me get rid of what I just did right there. That's just confusing. And I'm going to draw something then that's going to look something like that. As I read that from left to right, that function is decreasing, and it's clearly concave up. Okay. What happens then after we get to x equals -1? And I really don't like where I put that. After we get to x equals 1, now we shift into kind of this middle interval, right? Or I should say a second interval. So that was kind of interval number 1. Here's interval number 2, where x is greater than -1, but less than 0. And again, we've got to read both sign charts at the same time. In terms of behavior, we're into this middle interval here where g is increasing. And now in terms of concavity here, before we got to x equals 0, we're right here. We're still in this first interval of concavity prior to the first point of inflection at x equals 0. So our function g is now increasing, but still concave up. So I didn't leave myself a lot of room here, guys, but I want to make sure, yeah, that's decent, not great. All right, but that curve right there from left to right is increasing and concave up. Okay, now, in between x equals 0 and x equals 2, we are now onto a third interval right here. And let's read what's going on here. For behavior, we're still in this range here, guys. The function is still increasing, but we hit a point of inflection at 0. We're past it now, so the concavity has changed, and our function is now increasing and concave downward. So I'm going to try to connect these two dots with a curve that's increasing but concave down. I don't love what I did right here, but okay, fine. And then probably the easiest interval to read now would be the one that's furthest to the right. Behavior, function is increasing. Concavity, concave upward. So from this last point of inflection right here, we need to draw the continuation of this curve in a manner that's increasing and concave upward. And that is going to look something like that. Ladies and gentlemen, that is a function that I do not believe at any point over the last 1 or 2 or 3 or 4 years of math, you guys have ever been asked to graph without using a calculator. It's a pretty darn complicated one. It's a difficult 4th degree function that has this funky little bend in it right there, but it doesn't quite make the full W. I always think this thing looks a little bit like a grand piano, everybody, where, you know, you could just kind of draw this over here and then, hey, there's all your keys, and here's the end of the piano and that kind of thing. But anyway, this, I think that's bad what I just did. All right, this is a pretty darn reasonable graph of what's going on in this particular function, and we were able to get that by locating the points of inflection and all of the critical points and describing them as maxima, minima, or vice versa. And hey, just to show you that we're kind of on the right track, let me go ahead here. And I'm going to add a calculator page to this document here. No, that's not what I wanted. Let's try that again. How do I do this? I think if I hold that... heck, I don't know. All right, let's try it again. I wanted to add a graph page is what I meant. And we want to go ahead and just graph. Let me hit my up arrow, f1 of x, which looks like that. It's kind of what we graphed, but let's be a little bit more specific here. I'm going to go to Tools right here. You guys would hit your menu button, and I'm going to go to Windows Zoom and then mess with the settings a little bit. Now, the lowest x value that we had used was -1. So for my x minimum, I'm going to go just a little bit further to the left of that and go -3. The maximum x value we used was 2. Actually, I take that back. I probably should have made that a -2 to be consistent. The maximum x value we used was 2, so I'm going to put a 3 there, and I'm not too worried about my scale. For my y minimum, the lowest y value we had come up with, I believe, was a -21, so I'm going to put a -25 there, sure, just to be safe on that. And let's keep going then. The maximum y value we came up with was at that point of inflection, which I think was 6. I'm going to go ahead and put a 10 in there. You obviously don't need to be real precise on this. And when I hit OK, the hope would be that right now we're looking at something that more similarly matches the window that we kind of set up to graph, and it looks like this thing does a lot of what we thought it would do. This graph is obviously wider from left to right, but I feel pretty good about it. Another thing we can do that the Inspire CAS will do that the regular Inspire won't is it'll give us more detailed information if we come down here to trace, everybody. So if I go to trace, and we're going to do a graph trace here, I can probably take this point and drag it all the way over here. And if I go slowly with it, let's see if I'm right about this, it might tell us, everybody, when we hit, yep, there it is, if you saw it, a minimum. And look down in your bottom right corner, -1, -21 is the coordinate. I think if I double click that point, no, that didn't work. Maybe if I do a long press there, it'll actually label that point. Good, good, good. What else? It might tell us, I can't remember, if we hit an inflection point, it said intercept right there. Now that's where I think the inflection point was, but the calculator kind of took precedent there in saying, oh, it's an x-intercept. We think, though, that we have another inflection point that happened over here at the point 26. Let's see if it tells us that. Oop, I came off it right there. 2.6. It is not telling me that there's an inflection point there. All right, well, I tell you what we're going to do. If I double tap that and type in x equals 2, it should tell me that that is, okay, so we at least knew the point 2.6 was on there. And it definitely looks like an inflection point. But one thing you guys can do on your calculator, I'm sure I can here too if I can find it, is to go under Menu and go to Analyze Graph. And one of the things that the InspireCast will do for you is the 1, 2, 3, 4, fifth thing down on my menu. I don't know about yours. It'll find an inflection point for you. So I'm going to click that. Now for lower bound, I just go, here's where I think the point of inflection is. I just go a little bit to the left there. All right. And I hit enter on my keypad. For me, I'm thinking I just maybe double tap. Maybe I long press. No inflection with, okay, let me try that again. I think I messed it up, but I think I know what I did. Inflection point. So I'll pull that a little bit left and then just let it go. Upper bound. Okay, there we go. A little bit to the right and let that go there. And what you guys can see, it labeled the, oh shoot, it labeled that point 2.6 again. Yeah, that was our inflection point right there. So I feel really good about this answer that we came up with and the graph that we were able to produce. It's obviously not as pretty as theirs, okay, but it does what we needed it to do. The last thing I wanted to say about this problem is this should gel, this graph, everybody, with what you guys have learned over the last 2 years, going back to Algebra 2, about polynomial functions. Without doing a whole lot of analysis, you guys probably could have looked at this function and realized that this is a positive fourth degree function. The fact that it's an even degree means that your end behaviors are going to be the same. The fact that it has a leading coefficient that's positive means this graph needs to go up on the left and also up on the right. And the great thing about polynomials, they approach either infinity or negative infinity on both the left and the right-hand side every single time. And so that little bit of info seems to match well with what we came up with. As x approaches infinity, y is approaching infinity as well. As x approaches negative infinity, y is approaching positive infinity also. So it kind of passes the eye test too. And I bring that up because, guess what? Life's going to get harder. As we take a look at this function right here, f of x is equal to e to the x times the quantity x squared minus 3, this is what I would call a hybrid function. This is an exponential function, y equals e to the x, multiplied by a simple polynomial function, x squared minus 3. And this type of problem is outside the realm of any of the things that you guys have learned to graph over the last couple of years. You know how to graph exponential functions. You know how to graph quadratic functions, but I don't know that you know how to draw the two of them multiplied by one another. So what's going to get us through this? All of the work that we were just working on using derivatives and sign charts. So let's dive in, everybody. F prime of x. This, ladies and gents, is going to require the product rule. First factor is e to the x, multiplied by the second factor, which is, times the derivative of the second, which is just going to be 2x. So that's first times derivative of the second, plus the second factor, x squared minus 3, multiplied by the derivative of the first, which is still going to be e to the x. We're going to set that derivative equal to 0 and attempt to solve it. So the first thing I'm going to do is factor out the e to the x and see what's left over. That leaves me with a 2x plus the x squared minus 3. And I'm going to reorder that as an x squared plus 2x minus 3 is equal to 0. So we've started factoring, but we haven't finished it yet. So let's try to do that. Okay, one more time here. So e to the x then, and I believe, if I'm not mistaken, guys, that we now have a quadratic trinomial that factors into the product of two binomials, where the x squared becomes an x and an x. The signs, since c is negative, these signs are different. One's a plus, one's a minus. And I need two numbers now that multiply to negative 3 and add up to positive 2. We're going to get an x plus 3 and an x minus 1 out of that. And now we would set each of those three factors, first, second, and third, each one of them equal to 0, and solve. Well, as I'm hoping you guys can tell just by looking at it, e to the x will never equal 0. But x plus 3 will. That happens when x is equal to negative 3. And here, x minus 1 will equal 0 when x is equal to 1. So let's box those up. What we know for a fact right now, both of these are critical points. Those are values of x that make your derivative equal 0. What we don't know yet is whether or not these are extreme values, maxima or minima. And we won't know that, everybody, until we go ahead and complete the sign chart here and do some test values into the first derivative. So give me something less than negative 3. How about x equals negative 4? In between negative 3 and 1, how about 0? And greater than 1, we'll go with x equals 2. And remember, guys, right now, we're interested in behavior. That information comes from the first derivative. So we're going to evaluate f prime of negative 4, f prime of 0, and finally f prime of 2. And I don't care about the value, I only care about the signs. And so, going right here to the fully factored version of your first derivative is really the best place to go with these test values. I know you guys are scared of the e right here, but we don't need our calculator here just yet. Okay, so let's plug in a negative 4. E to the negative 4 is positive. E to any power is always positive. Times negative 4 plus 3, that's negative. Times negative 4 minus 1 is also negative. So that was positive times negative times negative. That is going to end up positive. And that means that our function is going to increase on this first interval where x is less than negative 3. Okay, let's move on to the next interval right here. When x is in between negative 3 and 1, and we chose a test value of 0, let's see what happens here. E to the 0 is positive 1. 0 plus 3 is positive. 0 minus 1 is negative. So positive times negative. Now we end up with f prime being negative. That tells us that our function decreases. And last interval now, greater than 1. So we chose a test value of 2. Let's plug that into the same factored form of the derivative. E to the second is positive. 2 plus 3 is positive. 2 minus 1, positive as well. Positive times positive times positive, last I checked, is positive, and that means that our function is going to increase right here. So reading this sign chart, everybody, at this critical value of x equals negative 3, our first derivative was positive and it changes to negative. That, everybody, is the very definition of a maximum. And that's how you test for it, too. So I'm going to go ahead and write that in there. We've got a max right here at x equals 3. Then, at x equals 1, prior to that, the function, I'm looking right here, guys, the function was decreasing. Afterwards, it was increasing, or better yet, I should have looked here. Prior to that, our first derivative was negative. Now it's positive. That tells us, everybody, that we are dealing with the very definition of a minimum right here at 1. Okay, so we're making some good progress right here. I'm going to run over to the next sheet right here, and I'm going to start making just a little bit of a list of what we know, guys. We said that we had a maximum when x was equal to negative 3, and we'll figure that y value here later on. We've got a minimum that happened when x is equal to 1, and again, I'll figure that y value out later on as well. The next thing we need to do, though, guys, we've pretty much learned everything we need to learn from the first derivative. Now we need to go to the second derivative. Now to do that, I'm going to take just a moment because I'm on a new page now, and I'm going to rewrite the first derivative. The interesting thing about this is, everybody, we actually have 1, 2, 3 different variations on how that first derivative could be written. Okay, the first one was what we got just using the product rule. The second is what we got when we factored out just the e to the x. And the third is when we factored the quadratic trinomial. All 3 of those are correct. So when I go to find f double prime of x, we need to take the derivative of the first derivative. Well, we could use any of those 3 forms. It's simply a question of which one would be the easiest. And I believe, everybody, that it's this second version right here, the one that's kind of semi-factored, let me put it that way, that's going to be the easiest to differentiate. Both of the other ones, the first and the third, would require doing the product rule twice. Once, oh, that was weird, and twice. And down on the bottom, you'd have to do the product rule here and then do the product rule again for the entire thing. I don't know what my hand just hit, but I've never seen that before. Anyway, back to this. So I'm going to rewrite just this second version of the first derivative, e to the x times x squared plus 2x minus 3. So let me write that out here. X squared plus, nope. Oh man, e to the x, here we go, times x squared plus 2x minus 3. Okay, so with that in mind, we now need to take the derivative of that, and that's going to require the product rule again. First factor, e to the x, times the derivative of the second, 2x plus 2, plus the second factor, which is the whole trinomial now, x squared plus 2x minus 3, times the derivative of the first, which is still e to the x. And I feel like now I'm about to regret where I wrote that information in red. Anyway, we're going to set this second derivative equal to 0 now to try to set up some potential points of inflection and try to figure out what this second derivative sign chart is going to look like. Doing the same thing I tried last time, I'm going to factor out the e to the x. Okay, and that's going to leave us with 2x plus 2 plus x squared plus 2x minus 3. That is going to give us an x squared plus 2x is a plus 4x, and a plus 2 minus 3 is a minus 1. So that's where we're at right now. Good news and bad news. What you guys might consider good news, this quadratic trinomial right here does not factor. We would need to find 2 numbers here that multiplied to -1 and added up to 4. There are 2 numbers that do that, just not integers, which is what you were probably thinking of when you said, no, there aren't 2 numbers that do that. There are. At the best case scenario, they are real and irrational. Worst case scenario, they might actually be imaginary. But what we're going to do then, guys, is we are going to use our calculator then to go ahead and solve this equation right over here. Okay? So I am going to go to, let's see here, my calculator page, of which I now have 2. All right, let's do this. All right, guys, and we're going to go to solve. So I'm going to hit menu, go to the algebra menu, and here we go. We are going to solve an equation that started off with an e to the x. So we've got e to the x, there it is, multiplied by, and now start a big set of parentheses here. And let's see if I remember what this was. That's going to be an x squared. That was strange. Let's see. Then I think, oh, now I forgot already. It was an x squared plus 4x minus 1. Okay. Plus 4x minus 1. Close that set of parentheses right there. We wanted that to be equal to 0. Need a comma now, and I wanted to tell it to solve for x. And if we're smart, everybody, because of the e's involved, we're not going to mess around with the exact solution. You guys would just want to hit Control and then your Enter button right now. For me, I just hold down Enter for a minute and go over here to squiggle equals. And we came up with 2 solutions right here. Obviously, I think those are irrational numbers. So we're going to round them to the nearest thousandth. My first is negative 4.236. So let me write that one out. X equals negative 4.236. And the second one was x equals, can't read that, 0.236. Oh, some connection right there. 0.236. All right, those are the potential points of inflection that we just came up with from the second derivative. So we make a 3-layer sign chart here looking like this. And once again, we're just going to choose 3 random x values that fall into these intervals. First interval, less than negative 4.236. So how about we choose x equals negative 5? In between those two values, just barely, we can let x equals 0. And then greater than 0.236, we can let x equals 1. Equal 1, excuse me. Now guys, we are dealing with the second derivative. That's where these values came from. So we are seeking information about concavity. We are going to put these 3 blue test values into that second derivative. Okay, so we're going to evaluate, did I do this in, yeah, I did that in blue before. Let's do the same here. We're going to evaluate f double prime of negative 5. Followed by f double prime of 0, and lastly f double prime, that was not good, of 1. And the only, I guess I could put them here, no, this is the best place to put them right here, everybody, the factored form of the denominator. So let's think about this. We know that e to any power, even negative 5, is going to end up being positive. The question is, what about this trinomial? Negative 5 squared is 25. Minus 20, that's a 5, minus 1 is 4. That trinomial is positive. So a positive times a positive is positive. That tells us that our curve is concave up right at the very beginning here. When we put in a 0, e to the 0 is going to be positive, but 0 squared plus 4 times 0 minus 1 is going to end up being negative. Positive times negative is negative. Our function is concave downward in that second interval. And now when we let x equal 1, obviously e to the 1 is positive, all right? But we've got 1 plus 4 minus 1. That trinomial is positive as well. Positive times positive is positive, and that tells us that our curve is now concave up. So if we look at the 3 concavities that we just came up with, we started off being concave down, right, because our second derivative was positive. Then things changed. The second derivative was negative, and we're concave down. So because the sign of the second derivative changed, everybody, we have a point of inflection right here at x equals negative 4.236. Continuing to move on, how about the second one? Prior to that, the second derivative was negative and the curve was concave down. After that, the second derivative became positive and the curve was concave up. So we have a second point of inflection right here at x equals 0.236. So I see now the error of my ways, everybody. I am an old man filled with regret. I think, nope, those are not even the same entity right there. Okay, what I am going to attempt to do, we'll see how this goes. Nope, that didn't work, is select, dang gummit, is select these 2 items. This shouldn't be that hard. Oh, there we go, got them. And I think I can cut those, and I'll come over to the next page, and I'm going to paste them in a similar spot right up here. And this actually works well for me that those are separate items, because I'd kind of like these to be in order. The thing that we're going to add to this list right now, in addition to the 2 critical points, are the 2 points of inflection we came up with. One at x equals negative 4.236, and I'm going to put that up at the top of this list, everybody. X equals negative 4.2, that's supposed to be a decimal point. All right, let's try that again. So a point of inflection at x equals negative 4.236 comma something. All right, and I'm putting that at the beginning of the list because this x value is less than either of the other x values that we've come up with. The second x value was positive 0.236, and that is going to slot right in here. We have another point of inflection at 0.236, comma, and we've got to figure out that y value there. So what I'm working on here in red, everybody, is the list of the 4 points of interest that we're going to plot in trying to graph this function. Now, because this function is so difficult to deal with, because it's this weird hybrid of an exponential function times a polynomial, all right, we're definitely going to need our calculator in order to do this. So let's see here. Let me go back to my calculator, and I tell you what, since I had that done anyway, and since I accidentally put in this second calculator page, I'll just use that because it's a little cleaner right here. Okay. So where are we, guys? Again, I want to define the original function here in this document here. So we are going to define, and I'm going to go ahead and just overwrite the f1 of x that I already had in there. I'm done with that previous problem, so we're good there. f1 of x is equal to, and then here we go, guys. This function was e to the x power, let's get out of that exponent now, multiplied by, let's see, right up at the top there, x squared minus 3. Okay, e to the x times x squared, and then a minus 3, and that should do it for the definition. Okay, what we're going to do now, everybody, is attempt oh, actually, now I just realized something right here. I'm going to go back, I lied, to this original page right here because I want to show you guys how to maybe get around having to type a number in manually that was not quite right. I'm going to go up here and I'm going to highlight that previous answer. I'm going to hit enter to bring it down. But what you guys are going to see me do is kind of work my way around here and delete all of the junk from that value right there so that I just have the number itself. And at the end of that, everybody, we're going to store that. And do I remember how to store on this app? Hey, I found it. It's under the variable menu. You guys have a button for that. We're going to store that first goofy value, and we're going to call that A. Okay, and it looks like we're done. I want to store the second ugly value of point of inflection here, that one. I'm going to store that into B. So again, I'm going to save just the number and get rid of everything else. Okay, there we go. And then, all right, we're going to store that one into B. So again, I go to variable, store, and we'll type in a lowercase b here. And this is really the way we should do it. The x values at the max and or the min, everybody, those were rational, if I'm remembering right. Those were, where were we? -3 and 1. So those ones we can type in. Okay, so what are we doing now, guys? We're going to go back to our calculator and try to figure out this y value by evaluating f1 at our a value. So let's go ahead and type that in. f1 of a. Ooh, I didn't want that capitalized, though. Does that matter? I'm not sure. Let's fix it just in case. f1 of a, and we will hit enter here, and we get 0.216. So we're going to write that down, 0.216. Got it. We're going to plug in -3 to get the y coordinate of this maximum. Might be easier for me to just go up twice, hit enter, and then just change that a into whatever I need it to be, which in this case is a 3. Ooh, and I got 6e cubed. No, thank you. I would rather have that as a decimal right here. So rounding that answer, f1 of 3 looks like it's 120.513. That is a big number there. Is that right? f1 of 3? -3. I think that was my mistake. That number did not sound familiar to me. So let's try that again, Mr. Fontana. f1 of -3. And again, give me the approximate. There we go. 0.299 is what that one looks like. So 0.299. Okay, now we're going to evaluate it here at this second point of inflection. That's what we called B in our calculator. So let's do that once more, and we are going to do f1 of B. All right, and so, yep, there it is. And we'll hit enter. And because our input value was a decimal, it gave me a decimal automatically then, -3.728. Gotcha. And the last one, our minimum, occurs when x is equal to 1. So we are going to evaluate f1 of 1 looking something like that. and is approximately equal to, okay, negative 5.437 is what we're dealing with there. Negative 5.437. Okay, everybody, this was a lot of work just to get to this point right here, and we're certainly not out of the woods yet, but we are in really good shape for what this graph needs to look like. Okay, so we now need to plot these 4 points of interest, everybody. And what's going on? Looks like my lowest x value is negative 4.236. So what I'm going to do is call this value here negative 5, and then just kind of go negative 4, negative 3, negative 2, negative 1, and positive 1. That's really as far as we need to go to the right. Wow, for y values, the biggest y value by far, at least in terms of absolute value, is that negative value that we came up with here in the last point. So I'm going to slide this up after all, you guys. I'm going to extend my y-axis coming down a little bit, and I'm going to say that right here is going to be a y value of negative 6. And then I think we'll just count everything out from there. Negative 3, negative 2, negative 1, negative 4, negative 5. And for positive y values, I don't need anything higher than a 1 located right here. Okay, so this is a pretty good setup. Let's work on plotting these 4 points of interest. Okay, point of inflection at negative 4.236, positive 0.216. Kind of a weird one, guys, but I'm thinking that might be roughly right about there. We've got a maximum at negative 3 and then positive 0.299. The important thing is that this point that I'm drawing right now is higher than the point of inflection because its y-coordinate is greater than that y-coordinate. Next point of inflection at x equals 0.236, so just to the right of the origin, and then down about 3.5, 3¾ units. So that's going to get us roughly right about there. And then our last point of interest, a minimum, is at 1, and then negative 5.5, roughly, is going to be right about there. Okay. Now, with those 4 points of interest, we also need to read our 2 sign charts simultaneously. And this is difficult to do, guys, but here we go. The interval farthest to the left is right here where the function increases. And the concavity interval farthest to the left tells us that the function needs to be concave up. So we need to draw something that's increasing and concave upward. Now, if you were to draw something that looks like this, you've checked those 2 boxes, increasing and concave up. But unfortunately, this problem gets just a little bit more complicated than this, and I really hate to make this harder than it needs to be. But if we were to think about limits, everybody, as x approaches negative infinity in this function right over here, the limit as x approaches negative infinity of e to the x is 0. This limit goes up towards infinity. So it's kind of like we're taking a 0 times an infinity, and who wins right there? But basically just realize this, everybody. Even if you're putting in a big negative number for x, e to that negative number is still positive, and x squared minus 3 is still positive as well. This value is going to be positive, but approaching 0 as x tends out towards negative infinity. And so, right now, I really don't like where I've put this. Let me see if I can move everything at once into maybe, oh, I didn't want that there, shoot. All right, let's try that again. Maybe if I can select all of this. Okay, this should do okay for what we need right here. Guys, I move that up so you can see that, and I lost my negative right there. Okay, so what we need to do here is draw a curve that's increasing and concave up, but it's also never going to equal 0, and it's never going to be negative. That's an asymptote. And so, boy, that sure isn't much of a curve that I drew there, but I think you guys can see that running this thing from left to right, it's increasing ever so slightly, concave up ever so slightly, and this thing is never going to hit the x-axis and is never going to go negative. Okay, in between this point of inflection and this maximum, what happens? Well, we have not yet gotten to this value right here, so we're still in this interval of behavior. The function is still increasing. But now we've passed this point of inflection. Now we're into this middle interval of concavity. So our function is still increasing, but now concave downward. So increasing, but concave downward would look something like that. Okay, we are now, oh, I moved some things here and this is ugly. All right, that is not what I wanted at all. We are now, yeah, something like that. All right, in between the maximum and then this next point of inflection. So what's happening here when x is greater than -3 but less than 0.236? So where are we? Still in the middle right here. Oh, I should say we've moved into this middle. Our function is now decreasing, and we're still in this middle interval of concavity. Our function is now decreasing and concave downward. So from this point to the next point, decreasing and concave downward is going to look something like that. Our penultimate interval, everybody, is greater than 0.236 but less than 1. So what's our behavior here and then what's our interval? All right, we are still in this interval here because we haven't gotten to 1 yet. So our function is still decreasing, but now we have moved on into, am I right? Yeah, now we have passed x equals, I've confused myself. We have passed x equals 0.236, this one right here. So we're into this last interval of concavity here. So our function is decreasing and concave up to connect these 2 points. So decreasing but concave up is going to look something like that. And now, everybody, that's it for the 4 points of interest. Now we just need to read the far right interval in each of these 2 sign charts. So again, I'm looking here. The function is concave up. Should have looked here first. And we're looking at this spot now. The function is increasing. So increasing and concave up is what this thing does all the way out on the right. And that is going to be a function that looks something like this. So everybody, that is a big old mess, but that is what this graph looks like. If you want to verify that by typing that into your calculator, go right ahead, but I feel like I've held you guys here long enough doing that. So that, if you haven't gathered, is a lot of work. That is why you're not going to have a ton of problems like that on homework, and you're only going to have one of those problems on your Chapter 4 quest. All right. They take a long time, and it takes a lot of work and analysis to get through there, and there's a million different ways you could go wrong, so you got to be real careful in how you do that. Okay, everybody, that is a whole bunch of notes right there, summing up what we've learned in 4.3 and 4.4 and 4.6. So dive into that homework. Good luck. Let me know when you guys have questions.